Hello, my name is Cortes, and this is my CFD project. What is CFD? CFD stands for Computational Fluid Dynamics, and is a science of predicting fluid flow, heat and mass transfer, chemical reactions, and related phenomena by solving numerically the sets of governing mathematical equations. Fluid mechanics assumes that every fluid obeys the following conservations. We have conservation of mass, conservation of energy, conservation of momentum, and a few more such as conservation of species. Stop that.
Slippery.
What is CFD relevant in? You have a few things in CFD. The results of CFD analysis are relevant in conceptual studies of new designs, such as mechanical parts. You also get a detailed product development as well, which helps the product made, and troubleshoot, as well as redesigning of a product. CFD analysis complements testing and experimentation by reducing total effort and cost required for experimentation and data acquisition. Different methods of CFD. Well, you have three methods to work CFD out. You have your theoretical work, which is working out CFD manually, such as doing it on Excel, getting the calculations out, doing all the equations. You also have experimental CFD, which is actually testing it through real life applications, such as through a car ramming into a wall, but you don't testing a car. And you also have computational work, which is actually using CFD software such as ANSYS. The pros of using CFD versus theory of CFD versus the others is that with theory work you get complex geometry. You also you have to wait for inspiration as well. The cons of it is you have no exact solution. You have a limited insight due to
CFD versus experimental CFD. The pros of using experimental CFD is that you have the possibility that there's a rapid turnaround, it's usually safe and less expensive, as you don't have to use different analysis on. It's very detailed and has powerful visualization, and the cons are the modelling uncertainty. You get that actually limit by available resources. It can be a problem with desperate length, time, skills.
CFD in real-world applications. CFD is used a lot in the industry, such as the automotive industry and especially the aircraft industry. It's used a lot in Formula 1 racing with the fluid dynamics, as you want to make sure the car goes as fast as it can, so it wants to be analysed through CFD as much as it can. Same with a NASA ship going into space. You want to calculate a lot of different CFD things with that due to it going in space. An example of the NASA example of CFD is the aero engine. Basically, the air goes through the intake or air inlet, and then it gets compressed into the shafts there, which make it go faster as it converges to that tunnel, and then it gets sucked in to that mini chamber, which then gets burned, and then diverges out, and then converges back in, gets burned, and then blows. Our project is similar in that concept where we're doing a nozzle, so we're CFDing a nozzle where it goes through it is convergent and it diverges there, supersonic speeds, and we have a third. So we're measuring that through CFD analysis. To start CFD, we need to take a few equations into account, such as temperature, area, pressure, density, velocity, speed of sound. As you see from the screen, I've done my results in a table with the different calculations. These are theoretical results to create the nozzle. which I used. I used all the formulas I needed, such as density, as well as constants such as gamma. And using these results, I managed to make some theoretical results for CFD, which I'll later analyse and compare with my results from computational CFD. There are different types of messages. You have 2D cell types and 3D cell types. In the 2D cell types, you get triangle and quadrilateral. The main one you want is quadrilateral, as that makes the mesh a lot better. With the 3D cell types, you've got tetrahedron, hexahedron, as well as a few others. But the good ones are the hexahedrons with four entities. There's a few examples that I've made on mesh types. This is in where you have triangles, and you've got a fine mesh over here as well as a coarse mesh. As well as different types of grids such as Cartesian, unstructured, and curvilinear. There's a few ways of improving the mesh quality. You can inflate it using the software ANSYS, as well as change the coarse to fine. However, this will impact the time spent on making the mesh, as well as making quads, the mesh type as quads. As you see, this is my first mesh I made, very basic, not that much of a course. The course is low. Is that wrong? Right, we'll cut that off. We'll cut that off. Cut that off. Cut that off.
Well, you can cut it.
Yeah. Oh, it's still. Are we recording still? All right. The mesh as well, as you see, has a dry inflation as well. In this mesh, I've made it more, added more layers, made it more smooth translation, as well as make the course more finer, which has obviously made the quadrihedron, what's it called? Quadrilateral mesh a lot better. To further make this mesh better, I've added more inflation, as well as made the course a little more finer to make this perfect mesh. This is another example of the mesh I tampered with, where I made the course a lot more fine, uniform quadrilateral, as well as analyze it so I can see how many good bits of the mesh are available. As you can see from the bar, it's a very good mesh, as there's not a lot of bad species. As you see, there's more examples of meshes that I've created using ANSYS, just to demonstrate different types of meshes you can get. As you see, the bottom left one is a fine mesh with inflammation, but it's not very consistent throughout the mesh, so it's not that, it has a few errors coming up, it's non-uniform. The top one is a fine mesh showing error removal, which highlights non-uniform areas of the mesh. As you see, the holes in the top, that's the non-uniform. And the bottom right shows a non-consistent mesh, and therefore isn't that great. As you can see, the inflation isn't consistent throughout and goes straight into a square, as well as curving in. These are my initial results that I created using my consistent mesh, showing the results, residuals of first iterations. And also from this, I was able to show the contour of pressure. As you can see, the top left of the mesh has a red point on it, which is where all the pressure is from. This is due to sudden directional change of the flow. To fix this, I have to make the start of the nozzle perpendicular to the pressure inlet. As the simulation is axis symmetric, we are able to mirror across the axes to show the full shape of the nozzle and flow through it. Show that. We can compare the results between the theoretical to the simulation results using temperature, pressure, density, velocity, and Mach numbers. that I'll do. This is the pressure results I got created through my nozzle. My temperature. My speed results. So comparing the initial results, bringing back the initial results we made, and the CFD results that I created, as you see, the line is very consistent, so it's a good theoretical result as well as, and it's the same consistency through temperature as well as speed. So it's been a very good CFD mesh. To conclude, I found that CFD is very useful in real-world life applications. It ensures dynamical equipment is fully tested before it's made, which obviously saves the company loads of money and time, as well as reduce accidents. The flaw of CFD though is that it doesn't take into account unpredictable things in real life, such as pressure, as pressure can change whenever, whereas the computer just calculates the pressure at a certain point and keeps it consistent. Also, through my results, I found out that the uniform quadrilaterals and inflation is more accurate when I create my mesh, and therefore I would use that for the nozzle. In the future, I would want to take it into a wind tunnel to test this even further in real life as an experimental CFD, as I enjoy the nozzle and would like to take that further. Thank you.
And cut.
Thank you for listening to my presentation. If there's any questions, I'll be happy to answer.
Yeah. Why is it less costly for companies to use CFD?
As it saves them money, because obviously if you don't have CFD, you have to make costly prototypes, and you'll have to use that, and if it goes wrong, then you have to make another prototype. It saves time and time's money, as well as making prototypes. So, yeah. Any other?
Why is it you haven't done a 3D CDF model?
Good question. That's because it's more accurate if I just do a 1D, as even though it's it's more conventional if I do a 1D model, as even though it's more accurate to do a 3D model, it's a lot more time consuming, which is you'd use in real life world applications like making a big 3D model. You'd rather just do a 1D and get a basic overview. That makes sense? Alright. Any more? Thank you for listening to my presentation.